This is 12.3.3 time dilation. Before we do any calculations in special relativity, we have to learn about what the Lorentz factor is. So Lorentz factor really just is a coordinate transformation from when you're looking at something from a different frame of reference. So the Lorentz factor, gamma. Gamma is equal to 1 over the square root of 1 minus v squared over c squared. Now very quickly, what I want you to do is I want you to evaluate gamma. I want you to evaluate gamma when you're stationary, so v is 0. You get 1 over the square root of 1 minus 0, which is 1 over 1, so gamma equals to 1. So when you're not moving, gamma just equals to 1. When you're moving at almost the speed of light, say for example at 99% the speed of light, then I want you to evaluate the value of gamma. Then I want you to evaluate the value of gamma for 50% the speed of light, so 0.5 times the speed of light. Then I want to evaluate it at 0.1 times the speed of light, so 10%. And you'll see very quickly that unless you're very, very, very close to the speed of light, gamma would normally roughly be equal to 1. And only when you approach the speed of light does it very rapidly begin to change. So for special relativity, we have to be very, very close to the speed of light. Now, we'll do the time dilation story. We get two clocks, identical clocks. We put one on a spaceship. So this is our spaceship with a clock. And we keep one of the clocks on Earth. We send the spaceship to travel near the speed of light for 2 years. And when the spaceship's clock has measured 2 years, it returns back to Earth. So, the inertial frame, or the frame of reference, is on the spaceship. And the Earth is the moving observer. When the spaceship returns back to Earth, they measure a different time. So where the spaceship might have measured 2 years, on Earth we might have measured 40, 50, 100 years. So we talk about something called proper time. Proper time is a time measured from the inertial frame of reference. So in this case, it's the time that we measure within the spaceship. So the time measured on Earth then is related to the proper time by t equals to t naught gamma. And that gives us t is equal to t naught over root 1 minus v squared over c squared. So t is the time for moving observer. And t naught is the proper time in the inertial frame. That's the end of 12.3.3.